Okay, Coffee Compiler Club here today to talk about compilers or porting mixins to Java or language type theory or compilers or garbage collection. I don't know what. Anything and everything to do with language implementations is fair game, and you're all being recorded live and you'll show up on YouTube within a couple hours. That's my starting spiel today. The people ask about my eye. My eye is doing fine. It has piles of floaters. This is normal, and they slowly fade over months. So suck it up, Buttercup. You just got floaters in your eye. I still occasionally get flashes. This is also normal, but nothing's getting worse. I don't have any obvious long-term effects, so I think I'm going to be fine. I managed to strain my gut during the procedure, and now my gut is sore, and sore enough to involve a harder look, but I believe it's just I basically strained an abdominal wall muscle. So no sit-ups for me for the next month. All right, that's it. I'm done talking about my bad health. Up until a year ago, I'd have said I was fucking amazing health. And everything falls apart. Fine. What else is going on? Next week, I'm flying to see my granddaughter in Philadelphia, so probably no coffee club. I'll see if I can internet it there. Jay Creed is going to be on in the summer. I'm looking way forward to that. I've on AA front, I backed off from some of my more aggressive typing things to try and get closure, and it's now, I think, closing in faster. I got a bunch of progress on the main stuff and found something funny, and I went back to the theory side and realized I actually had a conflict that wasn't going to be resolvable without sort of major changes to how the theory side was going. I was like, no, we're done here. I backed off from that. Well, that was the copy things need to be done as a value equivalence in the type side and not as a hack onto Henry Milner. So it's not it was not going to be a straightforward hack. It looked like it was going to be a good one, and then I finally found an actual counterexample. I'll give it up.
Are you doing global analysis in AA?
Yep. So we say global, you have to be more specific because that term carried different meaning to different people for over a long time.
It sounds like you have to look at everything before you can really get things going, and it sounds like it's going to be hard for performance.
Okay. So when you say performance, again, two different things. You mean compile speed or the
Yeah, compile speed.
Yeah, okay, fine. So what I'm doing is I'm doing a bunch of things that I could change that will probably get me more compile speed. However, my experience here tells me that this will not ultimately, I won't ultimately have a compile speed problem despite using Henry Milner. So the scanning is stuff, the forward flow typing things are all provably linear time. And I have done them in the past with excellent speed. So I am utterly not worried about them. To make it more complicated and maybe to make things slow down, it's harder for me to say at this stage if it's going to slow me down or speed me up. I am also incrementally typing as I parse, so that at any given point in the parse, I have as precise a type as I can have without knowing what comes in the future. Once that incremental time is done, I then run another global pass, and I say global, it means over the compilation unit, whatever the compilation unit is. So the compilation unit could be a function, a part of a function, the whole program, whatever the compilation unit is. I run typing on it, one more pass with Henry Milner, which has provably exponential worst case scenario, but in practice is almost always linear. Like you can write the exponential case, but you have to be writing a stupid program to hit the exponential case. That one I've also turned into an incremental work list algorithm, which doesn't help its performance, but it lets me do a sharper type analysis with the flow stuff, which is fast. So I don't believe I'll have compile speed issues. Having said that, I'm not super excited about having the sort of fastest possible compile speed. I want the generated code to run fast. I want my compile speed to be, reasonable. So something as fast as a typical C compiler would be well fast enough. I'd be willing to slow down from a typical C compiler.
Well, to my surprise, a typical C compiler actually is faster than Go, so that's pretty good, if that's what it
Okay.
is.
Yeah. So if I
Yeah.
was Go speed, I'd be fine with the speed of the compiler. Now,
Yeah, because when I heard that, you have to look at most of the program. Once you said compile units, that could be as small as a function. It sounds very reasonable. Because if you have to look at every line of every function across many files, because that's what I thought it was going to
right.
end up being.
So first of all, everyone supports, I'm going to support incremental compilation. So if you compile one thing, or at least as a minimum, I'm going to support incremental typing. You type one system, you set it in the library as a type thing. I'll re-inflate that back to an internal IR form with all the type info provably there. And that will be linear time and fast linear. That's an easy one. You know, this is the whole NP complete problem. I'm just gonna, once I've computed a difficult answer, I'll just record it, and then later you can pull it back out of the .o file.
It was kind of interesting that you said you're typing as you parse. To me, parsing just means lex, nothing else.
Yeah.
What does that? What does parse mean in AA?
So I hand roll recursive descent parser. Lexing is part of that, but that's a small part. No, I'm getting there. I convert that to IR during the parse, during the after Lex, you got some semantic notion of what's going on. You're doing a field load. So there is a pointer to reference and an offset. So field load gets done in the IR. Then I type the partial IR that I have. And it's an incremental typing, so it's not like it's super long. Let me find Ganesh here. And I run that till it's stable. Like I said, that's all incremental. So you add a small delta of new IR, you get a small delta of new typing. And I have the new type for what I have parsed so far. That's as precise as it can be in the absence of future unparsed program. And I repeat this till I hit the end of the program, and then I do the one more global pass with him and Miller. So I can get more specific yet with examples if you want. But this is like an extension of the C2 compiler work I did, at Hotspot at Sun and have done other places. It's just you build the IR, and then the IR can totally have all the program semantics right there. Well, you can run incremental constant propagation on it. And for me, incremental constant propagation is exactly flow typing. So I am flow typing by running incremental constant propagation.
And that part was the slowest part of my compiler. Like it just took up so much RAM.
So we can have a discussion about how to make that go fast, because incremental flow typing for me is very small amounts of memory and very small amounts of time.
Well, when I benchmarked my own code, it seemed like it was saying that 2/3 of the time was cache misses in the kernel. And unless I can make the kernel go faster, I have no idea.
Yeah, so I don't understand where you got cache misses in the kernel unless you're allocating furiously. Like your profile seemed very weird.
Yeah, I think I was doing something like I think 80 megabytes per thread, and the 80 megabytes in like 100 or 200 milliseconds. It was just hitting the page fault so often.
All right, it's Kaiser. I gotta take it. Sorry. Right. Hello. Hi, I'm fine.
All right, get the screenshot now for the new background.
Right.
Does anyone have any funny kernel stories?
Right. We're leaving on a trip.
Which stories?
Early next week.
Kernel, Linux kernel.
All right.
Yeah, I'm not sure if you were there when I shared this last time, but we hit this at work. So one of the Linux kernel patch is it increased the sensitivity of the TSC watchdog timer.
Okay.
And then that caused some nodes to spuriously fall back to HPET from TSC. and HBET is like way slower, and it's like a global platform level thing. So reading the current
How-
time became way slower.
How would you fix that? Yeah, I guess I missed it.
Yeah, a newer patch version, they weakened the sensitivity of the TSD watchdog.
Oh,
And then,
What do you mean with sensitivity? Is it's basically
so,
checking whether
there
it still
is a
gets
periodic NMI thingy that runs, that checks whether the TSC clock
is
source
still
is stable.
counting.
That if you reduce, I mean, if you have stricter thresholds on that, then you may have false positives that occur for that clock validation that may cause you to fall back to HBET, which is a disaster, right? So we ran into that, and then
Sounds like new chips got more complicated without necessarily good reason.
Yeah.
That was my follow-up schedule. Fine. Sorry for the break. Levo, did you get figured out here? Because what you're saying about speed to running flow analysis versus what you're talking about are like at conflict.
oh no. So it was kind of unrelated. You just said you can share some tips about speed, but my speed was mostly the kernel slowing me down, and that's why last week I wanted to like hear about kernel stories. And because I remember you telling me that you had some fights with the kernel, and the kernel slowing one of your programs down. So I was just thinking about that.
So I would have said that what your problem was that you were allocating 80 megabytes in a few hundred milliseconds.
Yeah.
And don't do that.
Well, I'm building the abstract syntax tree. I kind of need it.
Okay, so then your abstract syntax tree sounds extremely large. And maybe that's that I can help with. Or that's
that specific test was 2 million lines per, like trying to achieve 2 million or 3 million lines per second. It was like 20 megabytes of source. Actually, that might have been per file. So it might have been something like 100 or 200 megabytes of source. So that's why it ended up being so big. But it was just like a test I'd like to run.
Okay.
You allocate the nodes for the syntax tree separately, or you use some like bulk bump order thingy for the tree?
Well, I do a mmap for about 1 gigabyte, but I don't actually use the entire gigabyte, obviously. Actually, I'm gonna tweet it. I try to change things just to see what happens, and then maybe I can like figure out some performance gains just by observing what happens when I like fiddle with some knobs.
If you like mlock the memory ahead of time, then the rest of the profiles can be slightly cleaner. That may help you diagnose some other stuff, because if you like have the pre-faulting happening as you're running it, then it kind of like pollutes everything.
Yeah, I noticed.
Representative of the user equation total compilation.
I tried using map populate with a small amount, like unknown amounts I know I'll absolutely use, but it seems to slow it down. I'm guessing maybe it's because once it leaves the kernel, everything like the beginning of the memory is no longer in cache, and if you get faults as the program runs, the memory might still be in cache. Like I'm not 100% of what's happening, but I noticed not using map populate was better, and I was just hitting 2 faults per megabyte, and I have like a couple hundred megabytes like across all the files, so it's
Levo,
doing quite a lot.
if you don't need a global analysis and you're just trying to emit code, you should not allocate the whole program at any point. You should only incrementally parse and spit out code. And
I keep the data around because I'm planning to create a language server protocol, and it needs to know all the like if you do a rename, it has to look globally. So I kind of need that data around.
As soon as you want to keep it all around, you have to pay a minimum amount to swap it in and swap it out, and that's your limit. The only way to cut that down is to make your IR smaller.
2 faults per megabyte seems a lot to me, though.
When you say fault, you mean page faults?
Yeah, minor page fault.
Yeah, go to big pages. Sounds like you already are. don't allocate so much because you have a smaller IR?
Yeah, I was
Or
actually
you're just-
thinking
you're
maybe I
just-
can reduce it, but it's already like 3 million lines per second, so I don't really need to improve it.
Well, then don't worry about it.
Yeah.
Yeah, I was just hoping for like a simple like one line change that gets me because
No.
because I actually had a 3-line change that brought my code up from 2 million to
Yep.
2.8.
Yeah.
Just by 3 lines. I was hoping to find another one, but
No.
If you're
Yeah.
willing
Like,
to make
didn't get that
restrictions
lucky.
on your system or your use case, you can like pre-allocate shared memory pages and then permanently.
I
remove
actually
them.
I actually wrote a test to test that. It turned out I tried doing shared memory like in a separate process, and then my process grabbing the like a file descriptor and mapping that. It turns out it's just like much slower than just getting fresh
No,
memory.
not
I have-
not in a separate process. You can pre-allocate like 1 gig huge memory, like shared memory segments. Like
but this
in
is just
process-
like a Ganesh, this is just like a timing game where you say, first I'm going to do all the hard work of
Yes,
getting the
yes,
memory
yes.
faulted in and the page table set up and everyone cached in and out because the kernel has to zero it. And then I'll time my program,
Yes.
and he's blending the two, but the total wall clock time will not go down here.
Yeah, it did not
It
go
depends
down.
on
I
what
was just
you're
messing.
measuring, of course, right? And then how many times are you running the compiler and so on. So
Well,
the
I'm
shared memory
saying,
pages, you don't actually have to zero again because they're shared.
right, yes.
Yeah. So
Yes, if he can avoid zeroing the pages, that's because all his time is the initial memory because he's inventing from whole cloth from the OS's point of view, a huge pile of structured memory. And that's just minimum. You got to fault everybody. You got a TLB fault. You got a page fault. You got a cache
Yeah.
miss. There's no dodging.
I got lucky with 3 lines. I gotta like not push my luck. Like I should just stop.
Right. I think you're well past diminishing returns. If your goal is instead to just spit out code, there's something you can do faster. If your goal is to make a language server, that's going to run in the background while the IDE boots, and no one's going to care.
Yeah, that one function is like 60% of my entire time. So
Yeah. All right. What else?
well, I was like kind of like wondering about your stories because you said you had the kernel slow you down a number of times, and I was like wondering what those stories were. I don't know if you told them already, and I could just
No,
search
well,
them.
I've told them to this group before, but different contexts. One of them was VMware, virtual machine manufacturers, including VMware, deciding that the TSC register would be much more polite to use if it monotonically ticked forward at a uniform rate. So they intercepted the TSC. That made access to the TSC register about 100 times slower. Well, the TSC register is being used for things that were being called like literally a billion times a second on a large multi-core server. And you slow a thing that's being called a billion times a second down by 100-fold, it like kills your bench part. So that was one of the funny intercepts by the kernel. Like, why are you intercepting the TSC register again? So at that time we were using the TSC to prevent ping-ponging of a small cache. So one of the variants of an instance of cache can be updated. It can be updated by multiple threads. As soon as 20 threads on 20 cores are updating the same cache line, because it's a 1-entry cache, they're endlessly ping-pong the line. That's where your time goes. So you stall the update rate by simply putting current time millis or a TSC count, and people will look and they say, I have to wait. I don't bother to update. I missed in the cache. I do it the hard way. I look at the cache. Oh, the cache has been updated within the last millisecond or whatever. Don't update. And so if your cache is functionally useful, it gets updated once and everyone's happy. And if it's ping-ponging, it quits getting updated because it's not going to work anyhow, because too many different people want different answers out of the cache. So that prevented the cache from ping-ponging. And then the TSC slowed down by 100-fold, and the Go request to get the time for that slowed down by 100-fold. And that killed performance. So that was one. I guess the other one's a little more generic. We were trying to do Azul-isms trying to do low latency GC, which quickly turned into everyone blaming GC for every pause, and we engineered hard to figure out where the pauses came from, and discovered that their kernel was throwing lots of pauses in. And so we got hardcore about all pauses, not just GC pauses, and diagnosing where they came from. And sure enough, any normal kernel throws in a fair number of fairly egregious pauses if you're trying to do something below millisecond range. Actually, Arthur, you're here. You probably have more about this than I do. I'm throwing out generic stuff from when I was at Azul 5-10 years ago.
Yeah, I know that this concern exists. I usually don't deal with it because, like, we kind of shifting away from latency-oriented kind of applications. Like, it's latency-oriented applications is a very niche thing.
Yeah,
so we kind
I
of
thought you guys hit it big with the fintech, the high-speed traders, and
yeah, but it seems like we probably saturated that market, and now like the market is saturated. B, there is competition with other collectors in OpenJDK. Like maybe not, maybe the adoption is not yet there, but it will be. So now we are more focusing on like infrastructure cost saving and large applications where we can just by doing things more efficiently, we can let them use less, I don't know, Amazon instances to run their application and handle the same load.
okay.
So that is why we don't like, at least I don't see that many latency cases, and like we are not chasing this like last, I don't know, P99, 99, etc.
Yeah, I
And
knew
it's
you
tricky
guys.
because the people with large Java server deployments are also less likely to want to pay the per node or whatever fees that it's kind of tricky.
Oh, cost model. No,
Yeah,
they
that-
don't care as much for a lower latency pause thing.
Oh, no. I meant for the infrastructure cost. Like will Google ever buy Azul for their like hundreds of thousands of Java thingies? Probably not, right? Or,
Now we crossed that bridge a long time ago, and boy, Azul, fine. We actually did have an offer from
but
Google.
it works dramatically different when you're selling more than a few licenses to something. I mean, the way enterprise deals work is, someone from Azul goes out to dinner with someone from Google. They sit down, they have a couple bottles of wine, they talk some numbers, nothing comes together. 6 months later, they do it again. And then 3 months later, someone at Google like really needs it. So they just pick a random number, like 3.5 million, write a check, and it's done. And Google uses as much as they want for a couple of years. It's enterprise sales is nothing like retail. It's so unbelievably different that it's impossible to describe.
Yeah, that's what I know about it. Like I don't know much, but that's what I heard as well. That there is a price tag like on the website, but any real engagements like it, they negotiate and
Yeah, you have a price tag mainly because you have to have a basis for negotiating a discount, and no one will ever buy software at less than an 80% discount, generally not at less than a 90% discount. But again, that's not one CPU license or something. That's like as much as you want to use, but we estimate we'll use it on 1,000 machines. So we'll charge you for 1,000 machines and give you a 96% discount. And then you just make up the numbers until they fit the combination of budget, expectation from the sales guy on what his commission is going to be, et cetera. It's pure malarkey, trust me. But it works. Like
I'll agree with Cameron. I've watched the soup getting made in the kitchen, the sausage getting made.
Yeah, I had one unrelated question. So a long time ago, in one of the talks you, or maybe even here, you talked about the like cache profiling that you had at Azul. Is that just an artifact of like having the hardware simulator, or did something magical happen beyond having the?
There was a software variant and there was a hardware piece. So the software piece is we had no hardware for a while, so we made a simulator.
Yeah.
And then you got a simulator, you can run it for a while, and then you can tweak it up to slow it down to start collecting more and more and more numbers. And that led to like some really cool data race detection things. And I have an old talk that you guys probably never seen on a nearly infinite store buffer data race detector, which I used at the same time Steve Goldman was using to find bugs in Hotspot when you moved off Spark and x86 with their very conservative models, and some went to Itanium, which I did the initial port on, but I got out of there because Itanium, never mind. And then Azul, which had much weaker memory model. There were plenty of bugs in the runtime, and Steve and I were swapping back and forth with the bugs, and we were finding ours with this data race detection tool, which I can talk about if you want. That's its own little thing. And then because we had the hardware, we could do weird things with the hardware compiler co-design to get extremely large, 100% precise, extremely large cache traces. And that is somewhat of a trick, like you can't normally do that. So we would basically take a die and throw half the die away. So half the die is running, and that's already, the first run was 24 cores, but the second run had been 48, you know, divide by 2. So 12 cores to 25 cores are running, and they are replicating their cache requests in a second set of CPUs, who are then puking them out into an L2 cache, which is much larger than the sum of all L1s that are using that L2. And then that's getting streamed out to disk. It's getting compressed and streamed out to disk. So some of the cores are compressing, some are streaming, some are, you know, reading and writing, some are taking it from the active running guys. So the active running guys are actually not taking a slowdown. That's part of the main trick with that game, is that you normally, when you start doing cache profiles, the guy who gets profiled gets a massive slowdown that immediately changes how his behavior is and his profile data, therefore. So he gets like the wrong profile because he's slowed down by 100-fold to track his cache hit and misses. So we didn't have that because we replicated the cache traffic at the hardware level by putting the X links between caches in a funny state. And so requests to one cache went also to a second cache. And then a core CPU was only running in his core and not touching his cache, his memory at all. You can touch his L1, but not his L2, so no memory. Would stream his L2, read it, compress it, and write it out to another L2, and then somebody else was just reading L2 and doing network buffer filling. And you get these caches that were, you know, dozen to 25 cores running at full speed, doing full speed Java multi-threaded behaviors. So JBoss or WebSphere, what the fuck, doing J2EE things, all full speed. And you would stream out the decaches, decache hit miss rates, not rates, the actual cache stuff, out to disk as fast as your disk could swallow it. We actually purchased at that time some, you know, non-volatile disks, solid state disks. It wasn't what you call it's flash now, SSDs. Back then they had other names for it. It wasn't mainstream at all. But we did that, so we captured some of these things. So we'd have 10 billion long instruction traces that were actual live instruction traces with decache hit miss rates, and then you'd offline go and look at the data and discover things
like metadata to like map the physical addresses back to the like Java thingies, or how did you?
Well, most of that work was done by the hardware guys looking at hit miss rates.
Okay.
And we could do things like count the number of times an inline cache failed because it took a jump register. So we periodically would map them back. It was a big job to map it back to Java state, but you're looking at the core guts of a running WebSphere, and you've gotten basically a continuous flow heap trace. What do you do with it? So, you know, we were trying to make sure the hardware would do as expected, and the JIT was jitting out reasonable code, and we were looking for code patterns, and we were looking for hardware usage and the like, but not looking for how to modify WebSphere to be a more efficient thing. That was not
makes sense.
Right. So we had these giant traces, and we could tell you funny shit that you wouldn't have thought. Like that led to page coloring on our stacks, because of the L2 cache was shared on 8 cores with 4-way associativity. So if 8 of the cores all wanted to argue over the same modulus cache line, that would conflict at the 4-way associativity, and then there would be endless conflicts. All cores start at the same, you know, base address for the stack, modulo some large offset for stacks were offset from each other by however big the stacks were. That would normally conflict on the same L2 line if they were all running the same code. And so if you run a big single application and he does a big work list, they all run the same work list code. And right away, they're all colliding in the cache on the 4-way associative L2. So you did page coloring for the stacks, which means you just offset them a little bit. You bump them up or down. And then they would spread out in the L2 and not conflict, and that was fine. We did sensitivity on the sizes of L1s and L2s. And the answer was they're not. And once you fix stupid page coloring bugs, they weren't very sensitive. Like the jump Intel got from going from a 16K L1 to a 64K L1 was not going to be huge, except Intel also went to giant out of order so they could get more progress done in more clock cycles if they weren't, the incremental 5% reduction in cache miss rate goes further on an x86 because they can get so much more work done in the shadows of a miss. So if they can get rid of one more miss, they get a lot more work done in that shadow while they're waiting for the several misses or whatever to come back. So that was sort of the thing we found. Like we couldn't get doubling our caches was not going to give us a big gain unless we went to an out of order chip. So it was a 3 adjust risk in order. The second generation was dual issue. The main thing that was a big win that we could spot in the things was allowing a second miss to go in parallel with the first miss. So again, a non-blocking or non-lockup. It's one of the incremental steps towards out of order.
Mm-hmm.
You throw out a load, it's going to load into a register, you miss. One thing says stop right now, another one says run until I want to use that register. And there's another state that says, while that miss is going and I haven't yet touched this register, if a second miss happens, I get to start it as well. But every time I start another miss, I have to have another chunk of hardware that's tracking outstanding concurrent misses. So we stopped it at 2 because the difference between 1 and 2 was at the time it takes 1 cache miss to main memory to come back, I could get 2 cache misses. So I cut my average cost in half. Latency was the same, but my bandwidth doubled. But the third one would only be, 50% more, not a doubling.
Did the JITs know anything about like data structure always being a miss and then scheduling it ahead of time so it can use out of order?
No, there's a bunch of research work on that because there was a particular hot benchmark that did this kind of a thing. And if you relayed out memory with the garbage collector, you could arrange all those chained misses. It was a B tree like thing. You could arrange the chained misses to be chained hits or adjacent cache lines and prefetch your way forward. I never saw that in C2. I never did it. We looked, like there's totally a game that says we profile and we collect L2 misses to main memory. And we reverse those to Java objects to Java field loads. And then you decide that this field misses. So I want to prefetch it if I think I'm going to get there. And one of the things that comes out of that is typically by the time you've come to the point where you're about to go for a missing prefetch guy, the opportunity to prefetch it has long gone. Like you don't know you're going to need it until you're a few clocks away. And then a few clocks on a prefetch at 300 isn't going to make any difference. It's a 1% gain. Didn't minus 3 clocks off of 300, like no one cares.
Yeah, I had a feeling something like that. Yeah.
Right. So the better answer was a moving collector, just in general. If after a while things, the dead things, 90% die, the things that are old gen stick around, and that's the usual young gen, old gen, the generational collector rules work. 90% die young. Your allocations are all got holes of 90% of dead and 10% of live. And so you have these big holes between live objects after a while. The collector just smushes them and preserves their allocation order. The typical game being that the allocation order is somewhat correlated with the access order. And then if I access this guy, odds are I'm accessing this guy who's either on the same line or the next line over, and the hardware prefetcher starts to kick in and saves me. So moving collectors have a reason to be there. Having the collector be aware of chase ordering, like I chase this, and then this, and then this, and then tell the collector. So the next time the collector drags the visitation order in that way was a thing that we talked about, but I don't think we ever got there. Read bandwidth is limited. Yeah, there you go. Is a DCZVA a data cache
That's a zero
line?
cache. Yeah, that's the zero cache line one.
Yeah.
So I thought of I thought of a faster way to do memset, because memset is also limited by the read bandwidth, because if you write a non-zero value, it doesn't use the zero cache line. That means it needs, or at least, I mean, it doesn't have to, but it turns out that this laptop, it reads the line first. So the read is limited by the misbuffers. So I thought I could like do the zero cache line to get it like zero in cache and then like overwrite it with the non-zero data, but then that actually turned out to be slower. Maybe there's some like weird microarchitectural thing that's happening. But anyway.
Well, you probably ended up sending 2 writes out, one with a special kernel
I
plus the
technically
data.
don't need to actually send the write out. I can just allocate it as 0 in the local cache.
No,
At
no,
least
no.
that's my mental model. Then I could.
No. You when you do a DC0, it must, as a minimum, inform the other caches that this line they need to.
Right, but it doesn't need to write to memory just yet. So I would still expect
Yes,
just one write
but-
if the chip was doing exactly what I want. But apparently it's not.
But it still has to write to the other cores. And you could have been bandwidth limited on the ability to write to the inner bus traffic between cores, core to core traffic.
Or you mean like the Snoopy traffic? Who knows? Who knows?
Whatever QPC, whatever your interconnect does, it has a limited bandwidth. DCA is definitely going to have to send something to every other core saying evict this line. So Azul had a directory cache hierarchy that let them avoid sending to everybody. But you did go to the directory with a DCA who promptly told you that nobody had it, and so you didn't have to send it again. And that was, we custom built that hardware specifically for the case, because our thinking was we were going to data cache 0 every allocation on the planet. And it would statistically likely be not in anyone else's cache, but you had to force it to make it absolute, not statistical.
Yeah, I'll have to double check with the like non-temporal stores, because I know Intel chips, they have some like write commanding buffer where you can get this behavior even for non-zero data. I'll have to actually have a measure that though. I'll take note.
Yeah, there may also, right, Intel may also have a version that says don't make it coherent, and if it's a buggy, it's your fault.
Yeah.
Which works in specifically well-controlled situations, like the IO is going on in a certain way or something. And specifically doesn't work, here we go. Doesn't work for allocation because you don't know another core doesn't have or does have a particular cache line because in the past life it touched this object. Yeah. This is one of these games where we tried to get Intel to buy into our plan, and we just told them how it worked, and they were like, yeah, fine, thanks, get out of here. I go, okay.
Yeah,
So,
but then like when on my laptop, the GPU does have enough misbuffers, but they decided not to give them to the CPU, which probably makes sense for the workload.
yeah, GPUs in particular often have cases where they exactly know who has and who doesn't have a copy of the memory, and so they can just do non-coherent writes.
No, I was talking about the misbuffer. So if you read from the if you read from the GPU, you can get like 185, which is more than the CPU. So they decided to give the GPU more misbuffers, I think, for the reads, at least in my laptop. Anyway.
Yeah, okay.
I sometimes wonder if Nvidia would make a good CPU.
They have different trade-offs, right?
Yeah. That was the Azul model. It was the CEO of 3DFX.
I mean, if it's
3DFX.
Nvidia, they probably charge like 3 or 4 times the price of other CPUs, because then they'll be like, yeah, shortage reasons, we stuck an extra RGB light on it.
Yeah, well, the Azul was, we're gonna make a GPU like, we're gonna make chips, CPU chips like GPUs are made with, dozens to hundreds, eventually near thousands, and then have them run generic Java instead of having them run graphics. So they were low end, non-Intel, fast, easy to make, high volume, heading for a sweet spot of cost performance ratio, which they kind of hit, and then they missed because the market was faster CPUs only. Oh, 3DFX doing something new. Jim's pointing out 3DFX. Yeah, I don't know. That was Scott Sellers was the CEO of 3DFX at that time. Of course, my web's not going to load this page. Fine. I should look. All right, what else?
Oh, so I have a question for Arthur. So it came up like a month ago in the Discord. It was like, the question was whether Azul had a list somewhere of unfixable Java flaws. So like, if you were redesigning the JVM because you were writing your own language, for example, are there things that Java did that you would not do because
Delete hashcode.
Yeah, that's
Yeah.
one of them.
Yeah.
Yeah, don't have a list per se, but one of the things that like quite recently and often pops up is, for example, the way the caching of boxes in small ranges is phrased in the spec.
Yeah.
Like it is required that if you get value of a small integer, it's required to return the cached value, and it actually has identity implications. And I think when I discussed it with someone, they said that they seen a pattern where a small integer was used to synchronize on. So different parts of the system would take the same small integer and would take a lock on it. So it is annoying from compiler optimization perspective. If the spec allowed it to be like allocated if needed, it would be so much easier to do escape analysis on this one. So that's one that kind of pops up quite often.
I guess being allowed to lock or synchronize on every object, or do you think it's a minor thing because you're only paying for it if you really use it?
Oh, the ability to synchronize on any object, I think, is also sometimes annoying. Like if there was like just a separate monitor object which you can synchronize on, I think it would simplify things in the runtime. Just you don't need to carry the monitor bits in the header and do this like trying to squeeze all the information you want into the header.
Yeah.
Actually,
the heroic effort to squeeze the locks into the header has worked, but you still must lose some bits in the header that don't need to be there, and very few people actually get locks taken on them. So yeah, I would have said no locks in the header.
It feels like that.
Oh, actually, I have a good one also. So it is about interface types and verification of interface types. So in the spec for the verifier, what it says that interface types for verification purposes are coarsened to Java line object, and effectively, like there is no type checking during verification on interface types. As a result, there is no guarantee that when you're looking at an interface typed, field or value in runtime, that it will actually implement your interface. So by the spec, the bytecodes that use interface properties of interfaces like interface calls have to check the type in runtime. And the reason that was phrased this way is so because interfaces have multiple inheritance, figuring out the least common supertype for interfaces, like you cannot represent it just as a single type, single class or interface. It can be a set of them. So just, I don't know, for the sake of simplicity, I guess, when they wrote the initial spec for the verifier, they said, well, you don't verify them. And because of that, we cannot rely on interface types in runtime. And actually, there were a lot of bugs, both in our VM and hotspots in another VM that I worked on before, that you would trust the interface type from signatures, but you can actually concoct the code that violates this because the verifier doesn't check this property. And you're losing some performance because of that, because you have to do the checks in runtime.
Yeah. I spent a lot of effort making C2. In fact, at Azul, also specifically, I did a better job of an interface checking, whatever, optimizing interface checks, but you had to do them. Yeah.
There's also these weak soft phantom lock thingies. I read that they released a paper on the ZGC recently, and like half the paper is how they deal with the weak soft phantom.
Say again?
Weak
You're hard to hear.
So I posted in the chat, they released a paper on the non-generational version of ZGC, the new garbage collector in
Yeah.
OpenGL. And the CAPS paper is like the weak soft phantom ref implementation that they have. So apparently they all have to be like all the references, they have to be atomically cleared. That's kind of weird.
One time you have a concurrent collector, you atomic things show up all the time.
Yeah.
What is the, what do you, I couldn't hear what you were talking about as the issue.
The weak soft phantom refs, the fact that they exist.
Oh God, yes, fine. Oh boy, Azul, we spent butt tons of effort on those. Yeah, like people would be misusing them as well. And so that led to things that were correct from the spec, but only crashed on Azul. And if you write a weak ref to a cache and you discard your only strong pointer to it, and then you rebuild a strong pointer by looking it up from the key to get it back out of the cache, and you do these back to back where the Java code says write key weak value, the key is now dead. Then they say the value, the weak's now dead except from the weak ref. Then they say take the key and get from the cache. Between those two, a collection could run and throw your weak away, and you would get a null out, although the single threaded code back to back said put get. And no other collector was this probabilistically going to happen except the Azul collector, which is running full GC cycles every 30 seconds because we could. And then we would statistically likely hit this bug, and other people would die with an NPE because their weak ref went away and they were surprised. So they wrote valid Java code that depended on a behavior that was not common except on the Azul collector. That was, I don't know, I remember talking to Michael Wolf about, what to do with weak phantom soft refs, and I used to have them all memorized well, and the collector has to do all kinds of stupid shit for those. It's just, I'm sorry, I've ranted on this a lot before. Should stop now.
I think if try with resources was there from the beginning, maybe we could have avoided adding soft phantom. Who knows? Who knows?
Yeah, maybe. Yeah. Like C++ destructors did the job that try with resources is doing with just tons more, whatever, ceremony, fine. But the finalizers is really try with resources. Finalizers have all kind of bugs in terms of, the delay on the freeing up of an OS resource that's tied to a finalizer can be indefinite, and then you run out of the resource because the garbage collector makes a very bad cache maintenance protocol algorithm, and you're asking the garbage collector to decide when to free things and when to not, and he's bad at that. Weak refs had a different issue, but I guess they were all about the cache. It's still about caching. That's like, I made a giant cache. I don't know if I need these results ever. If the GC says I'm full, I should flush from my cache. I remember Michael Wolf going through large counts of weak refs and keeping an age count on them so that there was a minimal LRU-like behavior. If you didn't have the LRU-like behavior, you would flush things that people just threw in the cache, and then the cache wouldn't cache them. And so you needed age bits on live weak refs to give an LRU behavior, because the guy expected LRU behavior out of his weak cache. But like the garbage collector has no clue what's live for how long, when the last use was, and anything like that. So he's a really bad pick for trying to do LRU cache maintenance behavior. Fine. That would be a thing I would throw out of Java.
For the past month, I always been wondering how JIT writers would be if they were to write a JIT for C++ or just write an optimizing compiler for C++. I wonder how fast you guys can get it, because it feels to me that you guys have more experience optimizing, but I don't know.
I have certainly written compilers that were fast to generate code. And I would say on the era of hardware I had, because I didn't want to keep around for a language server, I was much faster than what you're doing. And on modern hardware, if I redo the same thing, it would be much faster because it's not hanging on to the code. The code wouldn't
Yeah.
any pages.
I meant performance faster, like compared to how fast C++ runs versus you're optimizing.
So, and then, you know, I did plenty of C++ compilers before doing a hotspot at Sun. That was, yeah, no, I was an old school compiler writer guy. Got out of grad school, PhD in compiler writing. Had a couple of jobs, one of them at Motorola doing their latest generation chips, whatever. It's all C, C++ code, no Java yet. And that was all benchmark wars. And I was in the benchmark wars against IBM and Intel.
Yeah, I'm not going to mention
Well,
his name,
a big
but
engineering.
go ahead.
The big engineering investment from the Go and whatnot, they're more concerned about.
Sorry, Ganesh, you cut off. And you have no sound now.
Capability.
All
Yeah,
right,
he cut off for me too.
Sorry,
Ganesh, try again. You got cut off for like 30 seconds.
Can you hear me now?
Yes.
Yeah, so I was saying that the big engineering investment into things like LLVM, they're mostly going into the speed of the generated code, not necessarily the speed of generation itself, especially when they have large machines to parallelize across. So the per,
Yeah, I agree.
Yeah, Simon, it's there. Ganesh, you do have a sound quality issue, and I don't know what it is, but I think it's on your end. Where are you located?
I am in California, but maybe the Wi-Fi is doing something weird.
Yeah, I think your Wi-Fi must suck. Or your laptop's running too many compiles in the background.
Who knows?
So
I'm not going to mention the guy's name, but one compiler writer told me that one guy can optimize as and get code just about as good as Clang or GCC, and just like one person could do it. That's what he said.
Wait, was it the same by code quality? Was it the same in terms of compile time?
All he said, it will be as optimized or better as present day Clang or GCC. He said one guy can do it.
Like you can look at what code it generates and then write your compiler to generate that code for that specific case that you're testing against. And then, yes, it will probably be faster and maybe better and whatever. But then you change one variable and it falls apart.
I mean, I taught Intel writing code out according to the function name. And so
like with these things, there's usually there's I guess a certain grain of truth. Like there are probably cases where you can at least definitely compile things faster. But
he meant performance.
Right. But so you also have to take out when people make those kind of claims, there's a bit of truth to it, and a lot of hubris, I think is the right word, or arrogance, whatever you'd like to call it. But this thing like, real developers can do it so much better. I was like, well, it's probably not so easy in reality.
Of the problems you're solving.
Is this the thing Levo actually mentioned? I mean, what I understood was the intention to say like every single person could do it, or there is just one person on this planet who could possibly be as good as Clang.
Like this compiler superhero, there's one person.
I think he was just saying that they're not that advanced, and a person could just figure it out given enough time and resources. Like one person could just you don't need a team to do it. You could just do it with one person.
Yeah, I mean the core question there is, I guess, asking where to cut the feature set and where to cut the effort.
I mean,
if you say, okay, you're like writing code generation for a language that is not as crazy as like C or C++, that's of course a lot of effort you're saving. Or if you have like a well-defined way to handle, let's say, undefined behavior or something, that's also like a huge chunk of effort that you don't have to bother with. And I guess if you have like a very, very simple language and you know all the possible code patterns, then you can write a more ideal code generator in a lot fewer lines of code, because I mean, a lot of the GCC and Clang code feels like people thought about a really cool optimization that applies to basically no code ever written on this planet, but they feel it's cool, and then it gets added, and then people wonder why Clang or LLVM is
That's
10
so
or
funny.
15% slower with each major release.
There's a
And-
clear set of optimizations that do it 95% of what you get out of GCC and Clang. That would be fast and easy, and it's totally what I did with C2 is just cut down to that piece. Now the other 5%, that's a long, slow haul.
Yeah, I think there's like a lot of sunken costs there. There was a long time ago, there was, I think, an article written by an author of a windowing system that explained why he will not add extra support for Nvidia proprietary graphic drivers. And I think the way he explains the sunken cost of basically making the code base more complicated really applies also to the compiler ecosystem.
Yes.
So
Yes.
I can give one data
Let me
point
see.
here. So with Falcon, our LLVM based compiler, I think so. It took from 2013 to 2017 to reach performance comparable with C2, and that was done by a team of 5 to 6 people. So 5 to 6 people, 4 years, and it was starting with LLVM, which at that time we considered the best starting point. So it's not that we didn't try harder. Like, I think it's just when you are trying to reach this state of well-optimized compilers, like it's hard. It's a lot of things you need to do. Yeah, you can reach some reasonable performance pretty fast, but then getting to the level of LLVM, C2, GCC, it will take time. And that story of like one person, it's not that complicated. One person can figure it out. It reminds me a story how at Azul we once interviewed a guy who on the interview said something like, "Yeah, I looked at the hotspot sources, like looks pretty bad. So if you hire me, I'll refactor everything for you." And like, well, how long do you think will take you like to refactor things? And like, yeah, a couple of weeks. I'll refactor everything for you. So that's what it reminded me of.
Oh, well.
Well,
We didn't take the guy, so we don't know what he could have done.
See, there's some point that says, a couple weeks, if he pulls it off, it's worth it. So just put a hard limit. Okay, it's 6 months. If you don't have it functioning, working, and it's better than what we have, then your job's over. But we'll pay you for 6 months, and then go to town, dude. It's a gamble. If he rolls, it comes up, you win.
A couple of years ago, I said that my prototypes are pretty fast, and it's faster than Go. And people are like telling me that once I have a real compiler, I'm not going to be half as fast as Go, and that I'll need a large team to even be up to the speed of Go. Currently, I'm 35 times faster, like multiple 35 times.
But
people are saying I need a team just to be as fast.
But you're not generating the same quality code. There's 2 numbers here that you seem to be using one number where other people think the other one. So you just need to be very careful here. There's how fast can you compile, and there's how fast is the compiled code run. And when you say these numbers, you need to be clear. You're very fast at generating code. Now, how fast is the generated code run compared to the equivalent program run by a C monkey writing C code?
If I'm using the TTC and Clang backend, they're both fully debuggable. So when I say that, I'm just mean debuggable code. Quality of optimized code, Clang is better than Go, and TCC doesn't have an optimizer.
So you're backing to TCC to generate the code when you're going in fast mode, and you're backing to LLVM when you're generating code for code goes fast as opposed to compiler
optimize.
Yeah. Okay. I think that would make a lot of things clearer to a lot of folks, because when you say stuff, it sounds unbelievably.
Well, let's talk about
unless it's
builds.
qualified. And as soon as you put those
like,
qualifiers in, it sounds a lot more sane.
think that makes sense if you have some like debug thingy that you want to do fast iteration and then but then you have like you generally don't want to use different compilers for like production and
So
staging.
there's a different story there, but yes, if I'm debugging code, I want fast turnaround, and so fast compiles are important. If I'm shipping
Yeah.
production quality code that has been well debugged in-house, do I take the risk of flipping backends in order to get faster code out and then get mysterious crashes in the field because there's semantic change, some, you know, where the undefined behavior got different between the two compilers and the like.
Yeah, all
Right.
your tests and your stage environments or whatever better use the one you're shipping for production.
I'm just saying, I have been in those situations and I've seen lots of folks in them, and the answers, you know, often come around. We are
But
not
doesn't that
compilers.
You have to get burned at least once for that, I think.
That
and
applies
then-
to all compilers, doesn't it? Because like debug mode in one compiler and optimized mode in the same compiler will get you also mysterious
I have
crashes.
definitely been in companies where we shipped debug mode because we didn't want to
Oh.
change the compiler. It was not important for the code speed to be that much faster. Like we would get a 50% speed uptick for optimizing. That was less important than stability. And we would just suck it up, but we didn't have mysterious crashes in the field. That was a key thing. On the other hand, I've been in systems where I was doing, like I said, I was doing benchmark wars against IBM. We pulled every possible compiler optimization in the planet out and ran the compiler in all kinds of funny modes that none of our clients would ever run it in, and we all knew it. You know, everyone on all sides knew that you didn't run profile guided optimization on production quality code.
I mean,
Bobby's grinning way there. Yeah.
Isn't stuff like this like a big contributor to the compiler complexity we're all struggling with? I think every engineering team would say, okay, we have this local optimum of performance versus complexity, where you say, okay, we're generating code that is reasonably fast in like 90% as fast as it could possibly be, and every percent improvement will cost us magnitudes of more complexity.
Right,
and I think
it's
it's never
yeah.
I think it's not the engineering team that says, yeah, well, let's double our code base for like 1% performance, but it's like the business people saying, well, we have a benchmark war.
I got told to
do it whatever it costs.
Marketing types, yeah.
Selling the compilers is one thing, but then if you're Google and you have like millions of machines, then there's also
yeah, they're actually saving money directly internally. There's a difference if it's my own dog food I'm eating to save myself money, as opposed to I'm handing it off to some other poor sap who then crashes, and then I, you know, reputation and money comes out that way. The Google situations, I think, are a little different. Yeah, and totally, I did the same math that you just said right there for C2 and said, all right, I'm not going to do all these fancy schmancy. I've been reading compiler papers as a grad student for, you know, a decade when I was doing C2, and I was like, no, we're not doing all this fancy shit. Instead, I did my own fancy shit, so that's fair.
Yeah, I have something that's vaguely related to this. Like I was working on my compiler's LLVM backend, getting rid of the interpreter. And I think in the spirit of being too productive, I decided to make myself unproductive by deciding, hey, I'm going to get rid of the LLVM backend. Basically, the sort of backstory there is I spent quite a bit of time like redoing my type system because there were too many bugs and I could no longer sort of hack my way around it. When I say redo, I mean re-implement properly, not like completely rethink from the ground up. After doing that successfully and surprisingly simplifying it quite a bit, started working on my LLVM backend again. And I decided, hey, we now have roughly, I'd say 70-80% of it done. It's not great. The code it produces is not great, but hey, it works. And for like a first step, getting rid of an interpreter, this is good. Like basically my whole point is I'm going to generate code as if I'm generating bytecode. Rather than immediately trying to make it the way you should do it. But the one thing I noticed there is that even though I am not really applying optimizations other than setting LLVM's optimization level, whatever that does, I don't know. Compilation was quite slow. So I timed it, and the equivalent of a hello world, I don't know off the top of my head how many source files it actually processes, but not a lot. In release mode, without optimizations enabled, takes half a second to compile. So then I was like, you know what, half a second hello world, I'm done. Because yes, there's probably a few ways I can make it faster, but no, like we're not going to do that. That's ridiculous.
Yeah, that doesn't sound right. I would say
probably I'm doing something wrong somewhere. Who knows?
so
But
for our pipeline, that is like 3 times 03 of like standard LLVM pipeline. For large methods, we would get like 100 milliseconds, like 500 milliseconds, maybe for like large methods. So we would be compiling a lot of code and pulling a lot of code through a lot of passes to spend half a second.
Well, are you
so
not...
the thing there is, it's possible because I do. Let me double check actually if the timing measures the writing of object files, but that's just writing byte stream to an NVMe, and I don't think that's going to take half a second. But
okay,
You're beating C#. C#
Sharp.
takes 2 seconds for hello world.
either way, point being, it took a while. So I said, hey, you know what? Let's take another look at this other backend I had considered before called Cranelift, which is written in Rust. And really, the 2 reasons I had dismissed it before is all 3. Documentation was quite poor. It didn't have support for like checked integer arithmetic, which I happen to require. And that's
check. Never mind. I thought Rust did check integer.
No, Rust does. Cranelift, this backend does not.
Okay.
There's no instruction in its IR to perform, say, a checked integer addition.
Okay.
Would you be open to TCC as your backend?
Well, so I considered C, and I very quickly was like, no, I'm not that suicidal, basically.
It's not that hard.
I'm not saying it's hard. Like the generating part is not the problem. It's everything else. Like very quickly there, the main reason is all the undefined behavior you have to be careful with. TCC itself is not maintained. TCC doesn't do checked integer arithmetic, so you have to sort of emulate it with 2's complement. And the problem there is compilers can just do whatever because it's undefined. So even if it works,
no. You could do check
unless you're using C23. Signed integer arithmetic overflow is undefined.
But the checks are not undefined.
So that's probably a case where it depends on the compiler. Like I know that if in Clang and GCC you write your checks in a particular way, the compiler's like, oh, this is a signed overflow check. We'll keep it. But it's one of those areas where you're depending on something that's not portable that might change. I don't want that, right?
Yeah, that's right. You're either choosing between inefficiently implementing it yourself on top of C or flipping a coin whether the compiler will do on some other platform what it accidentally does on.
Right. So I actually experimented with that. I had some basic code that did it, and there's quite a bit of pile of code where I was generating to C, and I had this helper function, checked that, whatever. And it said, oh, if we're on Clang or GCC, we use their intrinsic. If otherwise, we emulate it with 2's complement. And then there was a check somewhere in the header that said, like, hey, if you're not using Clang, you're not using GCC. And there's this one check to figure out if you're using 2's complement. If all those fail, we just don't compile. Like we throw an error, use a compiler that makes sense. But so there was that. There's the debugging aspect. Like if you generate C code, your debugger will be debugging C code. And yes, you have the line directives, but they're not going to teach the debugger to understand how to print your pointers or your whatever. And as far as I know, it's just.
You want that
I have a
connection? You're gonna have to, you're gonna have to talk to somebody's IR, not to C code.
Right. But so anyway, I wrote about it somewhere. But point being, I determined C is nice if you just want something quickly or whatever, or you're a C expert, right?
I have an answer to all of that, but I don't know because it seems like everyone dislikes C here, so I don't know if anyone wants to hear my answer to any of it.
In the least, in the worst case, we can rip it to shreds. So please go on.
Yes, exactly.
Okay, so the way I did it was I generated code specific C99 code specifically because that's what the TCC supports. But I did it with Clang and GCC compiling it because GCC, Clang gave me good error messages, and they both GCC and Clang both have sanitizers. So while I was emitting it, or when I was generating the code, transpiling, it would just tell me, "Hey, you did undefined behavior. Hey, this pointer is unaligned," and stuff like that. Actually, I don't think I ever got an unaligned pointer, but I was expecting that. So that basically solves the undefined behavior. Intrinsics, however, I had to compile with TCC, like my regular code, but I had to wrap intrinsics in a different, I had to have a function wrapper for the intrinsics and link using GCC or Clang because TCC does not support intrinsics. So that worked out until I used a Mac. Mac TCC dumps, it saves the binary in the ELF form, and Clang and GCC on the Mac does not understand ELF. So I could not use intrinsics on the Mac. So I might have to drop my TCC supports on Mac.
You got an ARM chip back in?
Yeah, ARM chip.
Right, but so to add there, that's kind of part of the problem. Like, you have to jump through all these crazy hoops. No,
It's
I'm
not
just going to use a
hard.
proper backend. I mean, it is. You have to do all this stuff where it's
It
like,
is
oh,
hard 'cause
we're going to
What-
use
What's a,
this
what's a
compiler.
proper back end?
Well,
It's
you got to
more
link
than-
your runtime, don't you? It's the same step.
No, not really. Anyway, so there were two questions there.
I want to know what
Proper
you
backend.
consider
So
a
proper backend would be something where like you generate 2 lines of code and there's not like 10 CVEs hidden in them right away, right? That's C. You basically have to be extremely careful.
No, the
Whether you
sanitizers will
write
tell
it
you.
or generate it with C, it's a minefield. And like I will sound a bit like a dick, but I think anybody who thinks otherwise has not written C in like a serious
I have
capacity.
certainly written C code and written auto-generated C to a compiler in the past, and I
Right.
consider it straightforward.
I
But
mean,
so ultimately my point was there, like you could probably do it if you're expert enough, comfortable enough, like you've written C for the last 20 years, you know Valgrind from the back of your head, whatever. I'm not that person, so I didn't want to bother with that.
One of the Clang developers were saying that they will not use undefined behavior if they don't report it with one of their sanitizers, and the undefined behavior sanitizer does a pretty good job. I don't think I hit any undefined behavior when I was using it.
Right, but now consider using a backend where you don't have to bother with any of that.
Yep.
Right, that was kind of
what
my
backend are
point.
you using?
So I was using LLVM. I am now switching to Cranelift. I'm basically
Oh,
porting 7,000 lines of Rust code for that. Fortunately, for the most part, that's
Okay, that's a
copy
different-
paste, find
different
replace
problem.
things.
Fine.
But wait, then in the representation you are using, you can still have undefined behavior. And actually, if you are doing a like reasonably low level compiler representation, you will likely have undefined behavior there, either specified explicitly like in LLVM, or it will be there implicitly just because like, yeah, you need this to separate some of the like checks from operations in order to do optimization. So I think at some point you just need to deal with the fact that, yeah, the representation has undefined behavior. You need to like use it correctly.
Well, what's the difference between undefined behavior and debugging your own compiler? They sound as difficult to debug to me.
So when I say that a low-level compiler representation will have a form of undefined behavior, what I mean here is that at some point in your representation, you would like to separate safety checks from operations that require these safety checks. Like you would like to separate division from the check, from the zero check, or like you would like to separate null pointer check from memory access. So once you've done this, you actually has an operation in your IR, like a load from memory, like a dereference, that without a check will not be correct. Like it would, yeah, that's where this undefined behavior comes from. Or you need to specify a specific behavior for these operations, but then you kind of have to integrate the check back into the operation. And you want to separate them because you want to optimize the checks separately from the operations.
C2 does this a slightly different way, which I'm hearing you skip over as an option, which is the load from memory carries a dependence edge to the check, which just forces scheduling of the check ahead. But the check can be optimized independent from the load.
Yeah, but then look, so now imagine someone is using this representation as a backend. No one, like, they will have to put this edge there. Otherwise, they would like encounter undefined behavior. Like you didn't
like
specify what will happen.
One line in the bytecode parser. I spit out a check. I spit out a load. When I'm spitting out a load, I have an address I have to put in it. I have an offset, a field name. I have to put in a check edge.
No.
Yeah, but then the
If
representation.
Yorick was to generate the IR graph himself, he has to remember to put that edge.
No, no.
Yep.
The load node will blow up at you and say, I don't have a check edge. No load is safe to make without a check edge. There can be there are a few load check edges that go to the root because they're available publicly, but the standard load says I have to have a check edge. You will fail during IR generation with an obvious bug.
So it means that
like that for every single possible undefined behavior that could occur, or some implicit, like
everybody who depends on a prior check for correctness, like divide by zero, loads and stores, and there are other things of various kinds. They have a check edge.
I think Java is slightly different than if you were doing like a C++ compiler. Maybe.
I'm sorry, say what?
Maybe Java is slightly different because it has less undefined like stuff than C++.
There's no question that Java has a well-defined model and that I'm forcing it. If I were to do this for C, I would require a check edge on my loads and stores, which I want the optimizer to clean out, but then I might end with more checks in a C compiler than a C compiler would specifically admit in exchange for having the undefined behavior become defined.
You need like a edge for like every signed add and a lot of little checks.
So I'm not doing sign, my arithmetic is not checked sign, for which were I to do that in a C2 style, I would add the check dependencies and overflow and push it all through the optimizer as teach the optimizer how to optimize it well, right? But it wouldn't be undefined.
So yeah, it's an interesting.
This,
it's an interesting mixture where you separate the check from the operation, but then you put a constraint and you say that if there is no check, then the IR is malformed. Yeah.
Yeah. And the check can be as cheap as, oh, the program started, so no check.
Oh, well, in this case, it is up to the user and like the one who produced the IR to make sure that at the beginning of the program, this like the legality constraint holds true.
That's correct.
And if it doesn't,
if I'm handed broken inputs, I'll produce a broken output. Yeah.
Well, but then it means that you have the concept of undefined behavior. You're just not formally specified like that. That's what I mean. Either compiler
right.
will.
The undefined behavior has to be global because I won't have any local undefined behavior. And if everyone else follows the same rules, we're good. You know, if you have a typed function argument that says it's supposed to be an integer and you pass me a float, it's broken, but you called in with a float instead of an int, and the typing system was supposed to have caught that anyhow. So something happened earlier on that broke things. You know, this is everyone plays by the same rules, then the rules work. But if somebody cheats, and then the rules don't work.
I think in general the alternative to using C does not have to be perfect, so it just has to be better than the way C approaches things. And I think from a ideological perspective, it's kind of a hard sell if you're designing a language which has very likely less undefined behavior than C, but then you're translating your well-behaved language into C as an intermediary step to then let a C compiler generate a native code that's again not as unbehaved as C. I think it's
All right,
I mean it's just weird.
Well, it just flies in the face of my long experience here. Many people have used C backends, and you can emit C code that doesn't have undefined behavior fairly straightforwardly. It's not hard to do. And then,
Sure, but I mean
It's
that's
very easy.
I agree.
It's very easy. Just don't use integers, don't use characters, don't
it's
use
like
functions, don't use
it's like
variables. I mean,
it's
just
not
emit
that
an empty
restrictive.
file. Just emit
It's,
empty file.
it's,
You'll be free.
it's a sufficiently smart compiler engineer argument again, right? I mean, yeah, you could do it, but I don't see like the whole point of it. If like I have a well-defined language,
no,
I want to
the whole
target a
point of it
CPU that's
is that the
also like
ability to spit
well-defined
out-
in most
So
cases.
Cliff, just a
The
mental
point is-
exercise, right? So we know that the same C code will produce two different results on two different backends, two different, say, chips, right? So that
That's true
means
for Java and many other languages as well. Java has plenty of undefined behavior baked into it, especially on multi-threading things.
So we're not
you're
in
saying it's a
agreement
good
that
thing. You're saying we should just dive straight into the jaws of undefined behavior and let it and actually use that as an intermediate function. So we pump data in,
No,
we get
not what
undefined
I'm saying,
behaviors
Cameron.
coming out. And now for each of those, we put them through
Cameron,
an
that's
undefined
not-
behavior function. So
not
we get
what I'm
just
saying.
completely random.
Cameron, that's not what I'm saying, and you know
Okay.
it. I'm
Yes, well,
saying
it's a mental
that-
exercise, right? Like,
No, for 40 years, people have spat out C code and had good performance and well-defined behavior out.
yes, but not on more than one
Convenient
backend.
way to get yourself up and running. It may not do everything you want, but it's certainly fucking convenient.
Yes, we know we can do it. It's been done. That's not the point. The point is now you have to test explicitly on every backend looking for
Yeah,
like all
and-
this.
and-
That's why that giant script exists where it's a giant
This is-
C.
There's like two fails in that statement there. These days, they're like two backends, ARM and x86. It's not true, of course, but there are two giant choosers of it.
Look,
the
I
other
just saw a
one
new
is-
backend for 6502 this past month.
Yes, but I'm not spitting out code for it because I don't have any paying clients that want it. Right? So the other piece is that this is just, you're going to get some undefined behaviors as soon as you cross certain kinds of thresholds. These standard single-threaded behavior is usually well-defined for everybody. You can make C code do it that has no undefined behavior. That's not a problem. It's been done over and over and over again. The
Yeah, it's really not that hard.
also true for lots and lots of folks. As soon as you're multi-threaded, all kinds of undefined behaviors show up.
I just find it amusing that we're not in agreements that undefined behavior and compiler bugs are equally difficult.
Yeah, I find them undefined behavior bugs to be almost, I won't say trivial, but fairly straightforward. Like the compiler did what? Oh, Jesus, what a cup. And then you go and change your code. Fine. Whereas the compiler bugs I end up dealing with take, days to
Oh,
weeks.
they take forever. Yeah.
Well, and I think that there are two different parts of this discussion. One of them is undefined behavior in a language for general purpose, and the other one is undefined behavior in compiler representation. And I think in the general purpose language, yeah, this is probably not the best thing to have. But in a compiler representation, I think you will have this anyways, either a formally specified or not formally specified, like Cliff said, well, if everyone is playing by the rules, everything is fine. Yeah, you shouldn't be emitting code with undefined behavior. So I think at the level low enough that you are using it as an input for a backend, you are bound to have it. Otherwise, you're missing some optimization opportunities.
I'm just
But
kind
you
of curious.
undefined behavior? No.
Uh,
If I'm spitting out code for a backend, I don't have to have any undefined behavior, and I'm going to get everything I can hope to get out of a C compiler minus the semantic gap between the language I'm writing and the.
But like you described, you have some, like, let's say you have a load that doesn't have a check associated with it, and you expect that the value passed into the function will be dereferenceable.
Yeah, I mean, in the IR I'm looking at, I would just put the check at the head of the function, the check at the head of the function. But if the caller of the function hands me a crap thing, then I'm going to do a crap thing.
Well, that's what I'm calling you. You still have this idea of undefined behavior. You have some set of rules you expect everyone to play by.
Yeah.
Otherwise, you don't promise anything. Otherwise, like, shit gets broken.
Yes.
And I call this undefined behavior, just not called this way explicitly and not formalized, but it's just set of like expectations or invariants that you expect.
So just to be clear here, if I were to write a go function to go dereference a pointer, and I handed that go function -17 as the pointer value, you think that Go would do anything different than anybody else, or pick your language of choice here?
I don't think that's what he's saying, right? Just that there exists things that you don't have checks for that are assumed to be true, and then everyone has to play by those. I think that's what he's referring to as. Not that any.
Yeah. So at some point in your representation, you should, like, it will become low level enough that you would have this notion. Okay, there is this expectation that you like never dereference a null pointer, that either it is checked explicitly or it is somehow guaranteed by the outer context.
I think it's not so controversial. It's basically saying that invariants exist and they matter. I think it's not any more than that, really, right?
The invariants exist, and if you don't follow the invariant, now you're undefined. Yeah, that's true. Every language, every typing system, everything.
Am I the only one here who has tried sanitizers on C and C++?
They're not 100%, right? So
I have tried them. Yeah.
Yeah, I mean, sanitizers are dynamic analysis tool, and any dynamic analysis tool is limited by coverage being not 100%. So even if you always use sanitizers, you never have a guarantee that you go.
I'm not going to say they're perfect. I'm just asking if you guys have any experience with it.
Yorick was setting as the bar, I think. Or
they're pretty good in my opinion. Like,
yeah, but it is dynamic analysis tool. It's just like testing. Of course, you will use it to rule out some easy errors, but you can never really count on this on being precise, because that's not the tool's choice.
The goal of testing is to raise your assurance. It's a useful procedure before you take money and make promises.
Yep.
But yeah, it never proves the absence of bugs.
And really, if you are using sanitizers, I mean, are you using fuzzing is the other question, because again, you need fuzzing to have decent coverage. I think if you're just compiling your tool with a sanitizer and just run this on a single code base or just run it on your test suite, you are probably not really having much of an effect from that. So I would claim that if you are not doing fuzzing with sanitizers, you are almost not gaining anything from using sanitizers at all.
Well, yeah, I got something out of sanitizers in the past, but fuzzing's a big step up. I'll agree on that one.
Yeah, fuzzing I have mixed feelings with. At the start, they were helpful, but then after a certain point, they just stopped finding things.
Same as sanitizers. Yeah.
Well, but they are also great at regression detection. Like, yeah, maybe in the not moving state, you run out of fuzzer bugs, but we find it very good at finding new regressions.
Okay. That's interesting, but I believe it. Yeah. I'm not complicated enough with AA yet to need a fuzzer, but that's definitely in my plans. Like I'm finding my bugs easier than that. But it's fuzzers.
Yeah, it's like sometimes when we get a bug report from a large application, would be actively looking into our recent fuzzer crashes, just because it's so much easier to there is a good chance that fuzzer found the same issue, and it's so much easier to analyze fuzzer generated test case.
Yeah. Yes. I bet you hand in hand with that is you can probably shrink the test case a whole lot easier.
Yep, we're doing this as well.
Yeah.
So I wanted to get back to this, I don't know what Arthur was trying to say, which I still don't really understand. So, so he was saying there's language level undefined behavior and then IR level undefined behavior. So like at the hardware level, right, there's no undefined behavior. Like there's only undocumented behavior where it says, like the Intel manual, it says like, you know, these bits of these flags are undefined and, you know, you don't know what they are and we won't tell you what they are. Or you have to figure it out by running the program yourself. But like, there's not
Bugs
like
too.
nasal demons where like you run this instruction and then like, you know, the computer explodes or something. Like I think there was a Pentium instruction that like halt and catch fire or something, but so that's the closest you get.
For
I mean,
modifying code, ARM has unspecified behavior. So that's kind of an interesting one. So if another core writes to code that you are executing, then the behavior is unspecified unless the instruction previously and before is one of a few, like nop, jump, and so on. So that will allow the chip to do any behavior that is allowed at that privilege level, and it's even defined like that in the.
But the theory is
Well, that's just more
permission...
undocumented behavior, though. It's not that it's.
Yeah.
I mean, it's
not
deliberately
documented.
undocumented. It's not that it's not. It doesn't, you know, leave the processor in a well-defined state.
Yeah, I mean that's like the I think the core difference in a language with undefined behavior. The undefined behavior is not local, but like your whole program is broken if there is like one line of undefined behavior in it. And even if the CPU had undefined behavior, it's not like, okay, now your CPU is broken, please switch off the power, switch on the power, and then you are in a consistent state again.
So the whole
I think that's the main difference.
So the difference is with unspecified behavior, it is contained to the operation you are like when you encounter this. But if we think that this kind of situation, like the reference of a null pointer, division by 0, if we think that they should not happen, like we just don't think that a reasonable program should have this, we can go further and say like, and yeah, just use the fact it should not happen. So we can optimize code around it, assuming that, well, this shouldn't happen. So if compiling and optimizing some code, I encounter division by 0, I just propagated the constant. If it is unspecified behavior, well, I have to still like generate all the code all the way until this point and then do the division and something will happen. But if I can assume that this should never happen, I can actually conclude, well, this code cannot be executed, it's dead. And I can actually prune part of the control flow graph reaching to this point. And that's how this effect starts propagating from the point where this occurs, like to wider, like to wider scope. Yeah.
And
actually, it just gives
a common. Oh, go ahead, finish up.
It just gives more flexibility to the compiler to make use this assumption that this should not happen. And if you say that it's unspecified, it is constrained to the point where you encounter this.
A common kind of C2 bug is one where either the optimizer has a bug in an optimization or you admitted broken IR to it. He proves false is true internally, then everything becomes dead and the dead code limiter eats itself up and the compiler halts with basically the empty function. There's nothing left in it. And that's just a symptom of the undefined behavior spreading non-locally.
Yep, and optimizing compilers are good at finding this kind of paradoxes and just eliminating everything. So yeah, like I've seen this more than once as well in a different compiler.
Yeah. All right. We all agree that compiler bugs are a bitch, or undefined behaviors are a bitch.
And also, I think another example that I like about undefined behavior and how it spreads. So in C, there's this, I don't remember the flag, but basically you cannot, you should use the pointer of the proper type to access the corresponding primitive type. So you shouldn't be accessing floats by int star and vice versa. And if you do this, it is undefined behavior. And the way this thing propagates and spreads is if you assume that if compiler assumes that you never access with mismatching types, it can do some aliasing based on that and say that pointers of different types cannot point to the same memory. But if you misuse the pointer, and if you start passing it around, it actually spreads to any point of your program. You can actually have a pointer to int that is in pointer to float variable. So that's how this thing, you did this cast once in one place, but then this value propagated and led to an incorrect assumption somewhere else, maybe in a different function. So that's another example of how undefined behavior spreads from the location where you first did that to the location where it was, where the assumption was taken advantage of.
It sounds like you guys have done C like in the early 2000s, where it's very hard to detect it.
I'm sorry, I've done C since when? The early 80s?
Oh no, I meant everyone else. They seem to hate it, but people that did assembly first seem to like not mind it so much, except for Cameron. He still hates C.
Oh, he's offline, damn it.
Yeah, I had no
Yeah,
issues
that's
with
just
C, but
modification, yeah. Yeah, x86 had to come through and beat on self-modifying code because people were doing it in the early days, and that was screwing with instruction prefetchers and then leading to funny behaviors on chips that were in fact the bad kind of unbehavior where you had to power cycle a chip.
I think even ARM, if you read this, I think you have to power cycle, right?
Oh, really? Power cycle, power cycle.
I mean, it doesn't say that, but what does it
Well,
mean exactly? You have to parse the legalese of this.
Yeah, but my expectation of how hardware is designed is that it won't cause the chip to go into a self-locked up mode where you have to power cycle. But you might throw funny exceptions that you're not catching, and the OS will kill you, and the chip's fine, and your process gets shot, and that's all good.
It's not obvious to me that reading this that it's contained to the process.
No, they probably don't want to say that it's contained in the process.
Yeah.
But the hardware designers badly want to contain it to, yeah. I have used chips for if you screwed the thing up. Actually, I have used them. I didn't do it though. I have seen chips in action where Intel, in fact, where you did the wrong set of funny instructions that actually burned the chip up. Literally, it was a halt and catch fire. Very literally, I mean, it wouldn't catch fire.
Wow.
The chip was, the magic smoke got out of the chip, and then you had to throw the chip away.
They should have dropped that instruction.
Yes.
So Levo,
Backwards compatibility.
Levo, I don't hate C. That's a kind of a silly binary. It's not hate versus love, right? It's like when you reach for a tool in your toolbox, right? You kind of hope that that tool isn't a chainsaw that's currently running with the button stuck on with the chain, rotating inside the toolbox, and you grab it, and your hand gets chopped off, right? Like, you have to know your tools, and you don't necessarily choose to use the ones that have the sharpest whirring edges as the basis for stability, right? So it's like when you want to build something that has predictable behavior and you have to build it on top of something that does not have predictable behavior, it puts a significantly higher onus on you. And I think Arthur was describing this pretty well earlier in some of the things he was saying. So, the reason you use C is to avoid, the overhead of some of the other options. But if you have to add the overhead back in just to make sure that the behavior is predictable, then suddenly it's no longer the same benefit. So. Anyway, I like to start on stable, predictable behavior as a starting point, and C generally is not that starting point. So while it's easy to spit out C code, it's not as easy to get back to a stable building block.
Maybe it's easier. It's as easy to spit out Go code and might be more well defined, as a for instance.
I strongly suspect that if you generate C code like SSA and then have the optimizer clean it all up, you'll get correct working code.
Actually, I think it might be like a fine middle ground. Just lower your code into representation with without undefined behavior, with explicit checks, and then have the optimizer of this representation to go through all the trouble in order to optimize the code and produce good native code.
Yeah, that's what I do because LLVM expects like something like SSA. Like you don't have to do exactly SSA. Actually, the way I do it, it's not exact SSA, but yeah, that's how my C backend looks like. Just because I did LLVM first, and it was quite simple. Like it looks pretty clean to me.
Well, LLVM has undefined behavior.
Oh yeah, that too. But
Right, but it generally tries to avoid it.
In C,
Well, it's what
You're
you
reading
put as an
actually-
input. That's
you're
what you
reading
get as an
Matt's-
output.
Matt's chat comment about LLVM and undefined behavior. This might be worth reading here. Basically, he's pointing out every major compiler backend typically ends up having an undefined or a poison in the
Well, that's what I was trying to say. That's probably said in a better way.
in C23, they even added an unreachable statement. So you can generate whatever you want. And then the compiler can assume that that code path is never reached. So any assumptions that would cause it to reach that code path are false.
That would be another undefined behavior hole. Yeah, in the land of writing hotspot in C code, we had that, but it was just a jump to throw an internal exception and die and enter the debugger, and you screwed up here. Called should not reach here. That's it. There's many switch statements. The default said should not reach here, but that was just a print and die in the debugger.
yeah, it's also that for me too.
But that's most programming languages, all of them, don't have a thing that says, I've not yet gotten to writing the code for this case, but I know it can happen. So I just want you to stop here and wait for the debugger because I'm going to go look and see how I got here and then understand the test case better. And I have to write that in whatever language I'm writing in for whatever system I'm writing for every time.
See, I had an issue with that. I don't know how to detect if a debugger is attached because it seems to me if I abort, like
You
it
can't
seems to me
tell,
that
that's the point.
you can't know.
You cannot know. That's the point. You have no notion of time as writing the language itself you're using has no notion of time because none of these languages do. Because it has no notion of time, you can't tell how long it takes to get from one program point to the next. And therefore it can be infinitely long. And then your process is owned by the debugger anyhow, so he can just God mode and read all your memory. And you can't tell in the language specific way. Now, if your program you're writing catches current time millis, catches the time, catches it again, sees a giant gap in time, something happened between these 2 points. Do you get stopped by debugger and restart it? You don't know. Did the OS switch you out and switch you back in? You don't know. Right? Did the Intel go into low power mode and just crept along for a little while before he picked up again? You don't know.
See, because I feel like I've seen programs crash and don't do like they crash and pull up the debugger, but they don't abort. And I don't know how they do that because I know how to exit or abort, but I don't know how to go to the debugger but not abort.
I have done this before.
Right? So that's the thing. Like I'm not remembering wrong.
Yeah, there's actually there's a clean way to do it on Windows and there's an ugly way to do it on Linux.
Okay.
Oh yeah.
I've seen the clean one on Windows and I've used the ugly one on Linux, but I didn't know what the ugly one was. So tell me what the ugly one on Linux.
What's the gist of the Linux one?
I think there's actually a call in the Linux API.
Is it new thing?
To activate the debugger from your current point.
I'll look that up after this.
I was going to Google it.
Yeah.
I think when I was doing this was like debugging hotspot. I think when I was doing this, the guys who did that literally kicked up GDB. They in the crash handler, they forked a GDB with the right kind of flags.
Yeah, that may be why it was ugly. Because in Windows, I think it's I think it's in the actual Win30. Well, wait,
It's in
at
the
time,
API
it's the
somewhere.
Win32 API. Yeah.
Right. Because I think this guy, then he went into a sleep. He said, you know, sleep a million years afterwards, and the debugger caught you while you were on the sleep. That's Levo's how you halt without halting, is you just sleep forever. Okay.
A funny thing that happened to me the other day was I generate C code and an LLVM LLVM backend, and I did optimize 2 on both of those, and it seems to me that it's faster as IR than it is in C code, even though they're both being compiled by Clang. So I thought that was a little surprising. I don't know why it's faster, but it's just faster.
Say
When you say
I missed the question here.
Oh, so I have a C backend with a TCC, but what I did was I compiled with Clang instead. So when I did my 2 different backends, it generates the code the same way because I generate to an IR and then have the IR converts to whatever backend I'm planning to use. So with the same IR to the 2 different backends, Clang compiled both of it. One is Clang IR and the other one is C. And the LLVM IR was faster than the C, even though they're both the same compiler.
There's all sorts of heuristics in.
But it sounds like you are short-circuiting the C parser, which in Clang, as far as I know, takes some noticeable amount of time. So if you go directly to LLVM,
No. I don't mean compile time. I mean produces a faster binary.
So and you're saying that if you are emitting LLVM IR directly, you get better performance of the generated code.
Yeah.
Oh.
Did you try to compare what the IR the parser generates is? That would be the next step.
Right. You just got a translation process issue with the C compiler.
See, I didn't care enough because I had other things I wanted to get to.
Yeah.
So I got to the other things, and it's on my to-do list to look into that.
Oh my God. Cranelift IR is called Cliff. Sorry. There's some pun here somewhere. Cranelift IR format, Cliff. They missed an F. All right.
I think the Cranelift people, they're actually taking a stance to rely less on like undefined behavior type optimization stuff. I think there were some blog posts about that. I'll try to find it.
Oh, I can imagine. If I'm doing a new backend from scratch, there's all kinds of stuff I wouldn't support, like undefined behavior in that sense. You know, same as we talked about before, if you garbage in, garbage out, but if everyone follows the same rules, then there's no undefined behavior. And yeah. Nope, I have to read Cranelift. Uh-oh. Somebody else has a double take on what now? FOSDEM schedule. What?
I posted the API call for Windows.
I saw that.
That looks very easy.
Is this my C2, Matt, or somebody else's C2?
Oh, there's
So it's somebody else's. It's of course an LLVM compiler, right? That's what C2 is.
Oh,
Everyone knows that.
Got it. Jeez. I did not come up with the name C2 either. That was not my fault. Somebody else decided on that one.
Yeah, I mean, if you were following all the standards, you would have called it JC. But apparently someone thought that was blasphemous.
Yes. What would JC do? Yeah, we can go there. The puns everywhere. No, it was the C1 guys had to distinguish themselves, and there had been a prior C0 that was post name, you know, got post sequel called C0. It hadn't been called that. When it was the JIT, it was called something else. And then C2 came along, and that was just me called it Opto. Because I took it from my grad student directory name I used to put the compiler in, was the Opto directory. Fine. Well, we're slowed down. We can be done. We've had, near 2 hours here. Anyone else want to say anything?
Yeah, I can't find the Linux example, but there is some, you go into some loop with a sleep.
Yeah,
Yeah.
I couldn't either. I've
You
been,
like, you
that's why I
launch
missed it. Yeah.
GDB with the proc ID or something. Like
There
it's
is
a
this
command.
library that does that. It's called libdebugme, and it launches GDB.
Thank you. That's what we're looking for.
That's
It's like
probably what I
um,
was looking for.
live to bug me.
I'm never
first right up.
surprised that Linux has the hard way of doing certain things.
Yeah, automatically
If
spawn
it's-
GDP on error. GDP
Yeah,
error.
Windows has the easy way of doing everything because all software on Windows comes from Microsoft. So therefore, like that API call I gave you, that only works with Visual C++. I'm sorry, Visual Studio, as they've renamed it.
Yeah, we started hotspot debugging on Visual Studio, or the precursor.
So when you have exactly one company providing all of the infrastructure software, it's really easy to integrate everything tightly together.
Well, it's a
I haven't
good idea.
I haven't used Kotlin. Is that like a proprietary compiler?
No,
Isn't it like open source even or something? And
Yeah,
they have
sure.
targets, not just the JVM. They have all kind of targets.
Does anyone know why they came out with Kotlin?
yeah,
Yeah.
because it's fun.
Well,
Why am I coming out with AA? This is fun.
so
Yeah.
they actually the story is they have a lot of JetBrains, they have a lot of Java code, they have a lot of like the IDEs in Java. At some point they wanted to write in a more modern language, and Java was slow, I think, before Java 7. So I think they used Scala, but had some issues with Scala as well. And they said, well, we have experience like building all the parsers and stuff. Like we can easily make a language that will be modern, have
Oh.
all the nice features. So it took them longer than anticipated. And by that time, Java actually got lambdas and streams and whatever. Now they are in this kind of strange state that Java has all these nice things and they have a different language. But that was the backstory.
They have, I thought I had a fair number of users too. I thought they were reasonably popular.
So they actually, it became an official language for Android. I think that was a big boost in their adoption.
Okay.
Well, because Google cannot call it Java and cannot say that they're using Java for Android. I think that was win-win on both sides. But yeah, people use Kotlin. I think there is this easy interoperability with Java, and you can gradually can start writing tests for your Java application in Kotlin.
Doesn't Jim use it? Jim, you on?
Jim's been on. I mean, he always has audio issues because he's in New Zealand.
Thought he was in not New Zealand, but Papua New Guinea or
Papua New Guinea comes to mind too. Yeah, some part of the other side of the world.
Thailand. Or...
Yeah, I don't know. What's my audio like? I haven't tested.
Oh, you're
It's good.
good. We were just thinking we
great.
were waking you up because you were asleep.
Yeah, I was doing something with audio, so I killed that. Yeah, Kotlin's got a front end IR and a back end IR. And apparently they take liberties to optimize whatever they think is clever between, your code and the IR and the other IR and the target. Chiefly, I think the innovation is the inline keyword that lets you, delete typing when necessary in so many different ways. That's my take on it. I'm unhappy about the kind of ivory tower. We're going to drag our feet as long as we like on certain features of the language, but they are progressing. There was some doubt, but I guess Google is a good tailwind for them.
Yeah.
They're somewhere on the TOB index. They're not high up, but they're not the end of the world. On the Java only language, on the JVM only languages, they're pretty high up.
Yeah, the TOB
Java
is,
has done everything Kotlin did. They put it in almost, current. The only thing is inline classes, where you can do something with a primitive type and make it a class, which is just basically, something for mix-ins by whatever mechanics. But yeah, Java has all the features of Kotlin now in experimental or whatever it is every time they put out a new release.
But Kotlin can
I'm-
do native code, I believe.
say what?
There's some native output option for Kotlin.
Yeah, I don't think anyone uses it though.
Yeah, I think they
Oh.
they could broaden their appeal if they focused more on their web native outputs. But I think, yeah, I mean that's pretty much like the one core distinction they have left from our JVM host language Java that's picking up some features.
There's no major failings of their LLVM Conan compiler except the tooling. Gradle sucks, and GDB on their Conan output really sucks. If I could even figure out where to get it. So I debug in Java, but the native executables do what they're expected under Gradle or EXEs.
I'll never touch Gradle again. Bad
Same.
project experience with Gradle.
So I think what's important there, native, like Kotlin native is essentially like a different language. There are some differences, not only in the standard library, like, yeah, you won't have access to the JDK, but I think there are some differences in threading model and other things. So like it is a language that looks similar to like Kotlin for JVM, but it's you won't be able to like take the same application and compile it into native binary.
Absolutely not.
I mean, it's fine. It's like if you're only able to take 98% of Kotlin JVM applications and run it on the web or natively, that's still a win compared to Java's 0% of applications.
Well,
and I think it really hurts Java a bit there that they have the spec and the test suite nailed down so much that it basically doesn't give them any wiggle room, and all the real world code written also means that even if they loosen the spec, they wouldn't probably have much wiggle room either to have platform specific or target specific differences. So yeah, I guess that's like the thing Kotlin can use as a benefit.
I don't know factually, but I have a feeling that it's far away from 98%. So I think it just like the syntax is the same, but at least like the standard library, you won't have the JDK there.
It's imported.
It's not like D where it's far less.
It's had dates for about a year now. It still has no standard IO. You can do print line, and that's the equivalent of system.output. And so IO is lagging. So that really cuts most things off. But there's also a JS target. So, what is the middle ground between JS and native and Java? There really isn't a whole lot. So that's a fun thing to look at. I don't support JS code, but I'm looking at a few things that might generate to JS for convenience.
So you definitely use native and Java backend.
Yeah, I wrote my own standard IO stuff, file handles, POSIX, models, and that stuff's not too painful. You're writing your own proxies and high-level interfaces, same as Java native code, where you put a native keyword or expect actual is the pair in Kotlin. And then there's, magical assembly.
Because
mean-
I only known people to use the Java backend, and I was wondering if it's like D and no garbage collectors. Like they have no garbage collectors, but no one ever uses it because it's too difficult.
They have made a not a tracing GC, but the old kind, and that's the last
Mark
release,
Suite?
1.8. I think so. And they had some crazy freeze where all your Android code was single-threaded until you froze it, so you could do multiple threads, which would throw page protection on any writes on any of the heap, which was, people didn't like that. So now they've figured out a little bit more concurrence. There's an atomics package, and C interop is fine. If you're not on Android, you can do C threads. No challenge, no issue.
So the guy who wrote the initial concurrency stuff on Android was Crazy Bob Lee. He wrote the thread local. I worked with him on it because he couldn't use the one from the JDK. He rewrote it at least 5 times.
Rest in peace.
Trying to get
It's
yes.
a real loss. I don't know what to say there. I mean, I met and worked with him briefly, and he's just a great guy all around.
Yeah.
Kotlin does borrow a lot of GWT, which I think Bob Lee was part of, like the main part of. So there's a lot of JS, which is pulled straight out of GWT.
Yeah, he never mentioned working on GWT, but I wouldn't be surprised. He worked on a bit of everything there.
Let's say he's pretty widespread there. Yeah, right. Covered a lot of ground.
Yeah, I guarantee he used it. I know he was using it for some stuff because he was actually, well, in his spare time, he had a bunch of things he had built on top of Android for his own home automation stuff. So.
All right. Well, I think we're losing people anyhow because it's 2 hours in. Any last comments?
I kind of do, I guess. So the reason why I brought up why did they make Colin is because I would imagine that companies would want like a better language. Like I don't know how many of you seen the syntax for my language, but it's fairly high level and it's on par on performance as C. But this like I never seen any other language that has high level syntax at the same speed as C. So I was wondering, like, I didn't want to write a compiler because I figured a company would eventually do it. But then once I realized that no one is planning to do that, I just did it myself. And I just confused why no companies want to write compilers.
It's not a profit center. That's a whole business model issue. It's really hard to make money in the tools game. I mean, IntelliJ, kudos to them, has been doing it for a long time, but there are not very many competitors to IntelliJ.
Right, and they only succeeded at it because they had super low cost labor.
Yes.
I know the founders. So
Oh, okay. Well, I mean, I just do the math from where they get.
Well,
their
they explained it to me. They They explained the strategy.
Yeah, I mean, I get it. So you do it for the love, or you get a big company who's like Google, who wants to make
There's
it.
so much development time you can save by having a better language.
But you can't get developers to pay you to do that, to make it. In particular, because your language probably doesn't make their life go faster for other reasons.
Right. I mean, like, it takes more time to evaluate your language and find out that it's good than it does to just write the program in a different language.
Yeah.
That is the unfortunate truth.
All
Yeah.
right. These are
Plus all the
good
plus all
open-ended
the
conversation for next time.
Yes, see you guys.
All right. And Simon will let you carry on next time, but I want to call it here.
Simon, do you have a screen filter on, man? You look like you're 12.
I know.
Sorry, I don't think so. I just shaved.
Just naturally look 12.
You look so young. It's incredible.
That's I just shaved. I mean, usually it's like all the hair is like not over there, but also over there. So
Boy Scout. You look like a 12-year-old Boy Scout. Excellent. Well, keep up the good looks because that's something you bet on until it goes away.
I just shaved too.
Yeah, I haven't shaved in a long time. Okay, bye.